Okay, now we're going to start getting into some pretty cool stuff. We're going to take all this, put it together, and look at modeling motion of a projectile, like you shoot a gun or hit a baseball or something like that. What's happening to this thing as it's flying along. Now, suppose a projectile is fired at a known angle alpha with initial velocity v naught, where v naught is a velocity vector. So this is saying what's the value of the velocity vector at time zero. Now we need to make two assumptions. First assumption is that air resistance is negligible. And the second assumption is that gravity is the only external force. Now we need to have these assumptions in order for our model to work. Now keep in mind that this is a mathematical model that describes the motion under these conditions, and modifying it for a few additional conditions is not a big deal if you're able to properly model those additional conditions that you're adding to it. Like there's more than just gravity working on it and that sort of thing. Okay, we can find the position vector of the projectile, which is kind of important because if we can find the position vector of the projectile, we can actually, at any time t, tell you exactly where it is. Not only can we tell exactly where it is, but remember, velocity and acceleration are functions of, or derivatives of, the position vector, so we can also quickly figure out acceleration and velocities. Okay, so from Newton's second law, we know that force equals mass times acceleration, which in this case, if I set up an axis system, so this is time zero, here's my projectile, takes off, comes back down, hits the ground. Okay, so here's time zero, the origin. I'm going to think in terms of obviously the x-axis and y-axis, but I'm going to think of this as positive j, as we normally would, and this as positive I in this direction. So at time zero, I'm going to have initial velocity vector. And the angle between this vector and the x-axis, this is what I'm going to refer to as being alpha. Now the total distance that this thing's going to travel will be here, to the point where it actually lands. Now, when I look at this thing, the force that's working on this is nothing but gravity. And gravity is working in this direction. So gravity is now going to end up, or the force vector is going to be simply a negative m times gj, where g is the acceleration of gravity. So g will either be 9 point, or the magnitude. Well, let me rewrite that. The acceleration then, or the magnitude of the acceleration, is going to either be 9.8 meters per second, or it's going to be 32.2 feet per second. Depends if we're working with meters or feet. It depends totally on what you're dealing with. So to take this idea a little bit further, I'm going to say that the acceleration vector, is really nothing more than negative gj. The negative g is the negative of the force of gravity, and it's in the negative j direction. That's why it's negative, because gravity's pulling it in this direction. Now, what just happened to mass? Well, you remember the idea of you drop a ball or a feather. With negligible air resistance, they drop at their same rate. So the acceleration has is independent of mass in a vacuum, and that's the idea of the negligible air resistance. So acceleration is really nothing more than negative gj. So my first derivative of my velocity vector equals my acceleration vector, which in this case is going to be negative gj. That means that my velocity vector is going to be equal to the integral of negative gj, that's a g, dt, which equals negative gt j, because remember it's still in the j direction, plus c. Okay, but we have the initial velocity. We don't know what it is. It's just represented by v naught. So I can take this. I can say, all right, negative gt j plus c evaluated at t equals 0 is equal to v naught, my initial velocity. So when t equals 0, this component goes away. That means that c must be equal to my initial velocity vector. So what does that do for me? Well, that tells me that velocity, my velocity vector, is then going to be equal to a negative gtj plus my initial velocity vector. Well, this is simply another way of writing r prime. So remember, the first derivative of the position vector is velocity. That would then mean that the position vector, r of t, must be equal to the integral of negative gtj plus v naught dt, which is equal to negative gt squared over 2j plus v naught t plus c. Now this value of c is going to be 0 because at time 0 my initial position is 0. I haven't moved anywhere. I'm right there at the origin. So c is going to be 0. So that will simply give me r of t as being equal to negative g over 2 t squared plus v naught t. Now I want to take a look at this initial position vector v naught, because obviously in this form, oops, I forgot my j again. I keep forgetting my i's and j's. There we go. Obviously in this form, it's not going to do much for us. So if we denote the magnitude of the vector v naught as simply equaling v naught, and when I refer to this as a scalar, I'm going to try to put a little, make it like more like the Greek letter nu. I'm going to put a little tail on it. This is a scalar. It's a function of t, but it's a scalar. It's no longer a vector because I took the magnitude. With that would apply that v naught, the vector, if I break this up into component form, this is going to be v naught, the magnitude, times cosine of alpha I plus v naught sine of alpha j, because this initial velocity vector is going to have a component along the I-axis and a component along the j-axis, which is obviously going to be cosine of alpha and sine of alpha multiplied by the magnitude of v naught. So with that, we're basically done, because now what we have is the ability to write r of t, the position function. This all tells me that r of t, this position function, is going to be equal to, let's bring our i's in here first. I've got v naught cosine t, or cosine I. Oops, I did forget the t. Right here is that t that I forgot. that t needs to come back in here, so each of these is going to be multiplied by t. See this guy here, v naught t? Okay, so that gives me my position vector as being v naught cosine of alpha times t I. This gives me my horizontal component, plus, if I take a look at my vertical component, those are the j's. That's going to be v naught, I'm going to pull the t out here, v naught t sine of alpha minus g over 2 t squared j. So what that gives me is I can write the parametric equations that describes the motion. So the parametric equations are x equals v naught. Yeah, remember I said I was going to do that. This is not a vector. See, v naught cosine alpha t, and y is v naught t sine of alpha negative g over 2 t squared. So now for any time t, if I come up here, for any time t, I can tell you where it is along the horizontal axis and where it is along the y-axis. So I can pinpoint this location with either a position vector or parametrically, whichever works out best for whatever it is I'm doing. Now, one thing that's kind of obvious I'm going to want is, what's this distance d? In other words, when's this thing going to come back down and hit the ground? Well, I can actually solve for that quite easily by simply noticing on my graph that I'm going to hit the ground when y is equal to 0. So if I take a look at these parametric equations, I say, all right, I'm going to hit the ground when y equals 0. Now, obviously, I don't really care about it at this point. I'm really looking at this point because this is a quadratic, so clearly there's going to be two answers to it. So if I take v naught t sine of alpha minus g over t, whoops, not a double negative, minus g over 2 t squared, and I set this equal to 0. If I factor out a t, I'll have t times v naught sine of alpha negative g over 2 t equals 0. Well, clearly when t equals 0, the whole thing's going to be 0, but that's that initial one right here, which I really don't care about. It's this guy right here that I'm looking for. So what I really need is I need v naught sine of alpha minus g over 2t to be 0. That would imply that, see, v naught sine of alpha, that's twice that, over g is equal to t. So when t equals twice v naught sine alpha over g, then I'm going to be back on the ground. So given my initial velocity, because remember I would know this, and this is not a vector. If it was, I'm still writing arrows when I'm distinguishing between them. This is a function of t, but actually the initial velocity would be at when time is 0. But this is going to be a number. Sine of alpha is going to be a number because you're going to know alpha. G is going to depend on what system you're using. Are you using a metric or English system? So are we talking about meters per second or feet per second? And that will give me the time that will occur. Now, an obvious question I think to ask is the age-old question you've probably seen a zillion times of what angle should I set this at? What angle here that would maximize my distance based on obviously my initial velocity? So I want to maximize this. Well, you can see right away that sine of alpha, that's what's going to result in maximizing this thing, is the value of alpha. And So clearly, alpha is going to be somewhere between 0 and pi over 2. But that doesn't make a lot of sense here. It looks like maybe, well, actually it does, because pi over, it looks like I want to be at pi over 4. Well, I don't know. Pi over 2 should do it, because at pi over 2, sine is going to be 1. That would maximize this, but I don't get it. Why would this angle be up here at pi over 2? Well, part of that is because we're looking at y. So let's put this in for x and think about what's going to maximize x. I'm not trying to maximize y. I really want to maximize x, which is my distance. So when I put this in for time, I will get x equals v naught cosine of alpha times t, and t is going to be twice v naught sine of alpha over g. So this is going to be, see, twice v naught squared over g. I'm going to move this 2. See, v naught squared 2 times sine of alpha cosine of alpha. See, now we're getting somewhere, because this equals v naught squared over g times, see, 2 sine alpha cosine alpha. That's the same as sine of twice alpha. Okay, now this makes sense. Because alpha is pi over 4. Twice alpha gives me pi over 2, which is exactly what I want, because sine of pi over 2 is 1. So that will clearly maximize this. Any other value for sine, absolute value would be less than 1. So I'm going to have some value less than v naught squared over g. But when all of this is equal to pi over 2, then sine of pi over 2 is 1. So clearly alpha must be pi over 4. So if I set this angle to pi over 4, that will maximize the distance. So with some of these actual values known, if I actually knew some of these values, then I could figure out how long it's going to take to land, use that to answer all kinds of different questions, which we'll take a look at in the next example.